This chapter is about the basics, lots of concepts and definitions. Of course, it would be crazy to confront them all in one hit like this, but already some of these you'll be a little familiar with: statistical inference, sample, estimation, open science. The key, I think, is to take it slowly and to figure out how they each make sense and how they fit into the story of research. That's our story of asking questions, collecting data, analysing and drawing conclusions. There are goodies, glossary at the back of the book, and these goodies at the online website to help. Have you made this website a favourite or bookmark? And also have a look again at this section at the front of the book, which has evidence supporting various advice about how any of us can make more effective use of our learning time. One of the key points of this chapter is expressed by Richard Feynman, the famous Nobel Prize-winning physicist. Don't fool yourself and you are the easiest person to fool. Well, indeed, we all have the tendency to leap to conclusions, but the DFYs, the doofies, this is a number of cautions, a number of things we really need to bear in mind all the way through. I'm going to make brief comments about three major issues in the chapter. The first is sampling and drawing inferences at the heart of how we do research. We ask research questions about a whole population, perhaps all of humanity. We collect data just from a sample drawn from the population, and our statistical model, our statistical assumption, is that this sample has been chosen randomly from the population, meaning that every member of the population has an equal chance of being selected, and that we select all these people separately, independently from the population. In practice, we can rarely achieve a truly random sample and have to make do with a convenience sample, a practically achievable sample. Then the question is, do we have bias? Was our convenience sample selected from the population in some way, considering what our research question is, in some way so that the sample is not representative of the population? And if we think there has been bias, then it's not justified to draw an inference back from this sample to the population. It's a matter of judgment. If we judge our sample has been selected in a way that means it's reasonably representative of the population, then we can go ahead and calculate from our data the sample statistics we're interested in, for example, the average, the mean M, and then use that as a point estimate of what we really want to know, which is the population parameter, the corresponding mean mu, Greek letters for population parameters. So we know about the sample and the sample statistic, but we don't really care about them except to the extent they tell us about what we really want to know about, the population. The second major issue is measurement. We use numbers to represent things we're really interested in. So a 3 and a 6 might represent different levels of anxiety or different amounts of time to complete some task. Whenever we see a number, a data point, we need to bring to mind what does it really represent. And it's the anxiety or the time that we're really interested in, not just this number. We identify 4 levels of measurement here. The lowest is nominal or categorical measurement, which makes use only of the identity of the numbers, whether they're the same or different, not their sizes or even orders. So if we have 3 sports shirts in the laundry, say 2 with a number 3 and 1 with a number 6, then we can say those 2 shirts belong to Mary and this one belongs to Susan. It doesn't make sense to average these numbers or even say that the shirt with a 6 is bigger or better or newer or more costly than the one with 3. At the other end of the measurement scale, ratio measure, then we do make use of the full range of characteristics of these numbers. So if we have 6 cherries on the cake and 3 cherries on that other cake, then we can say, well, we've got more cherries on this cake. In fact, we have twice as many cherries here as we do on that other cake. And it makes sense to average them or give a ratio, whereas with the shirts, the numbers on the shirts, it certainly didn't. In practice, most often we're debating, do we have ordinal or interval level of measurement, ordinal or interval scaling. And this is the example I use of a Likert or Likert item, where we ask people to express their strength of agreement or disagreement on some question, some statement. Clearly we have ordinal scaling because, just by definition of these terms, a 6 means stronger agreement than a 5 does. But interval scaling needs more. It needs distance. It needs the assumption that the interval from 4 to 5 is equivalent to, the same as, the interval from 5 to 6. So the amount of difference in agreement from neutral to agree is in some sense equivalent to the difference from agree to strongly agree. That's hard to think about, isn't it? In fact, it's probably a question which there can't be an absolutely certain right or wrong answer. We just need to be conscious that if we're going to add up or calculate an average of scores like this, then we necessarily are assuming that these equal intervals apply to the scale that we're using. In other words, we can manipulate the numbers here, but we need to think about what's happening to the concepts underlying those numbers. And that's the key question for measurement. The third major topic is selection, and the way selection can mislead. Our open science slogan is, we need the full story. And there are 3 ways I mention where selection can mislead. One, most obviously, is if only some studies are reported, only selected studies are reported. Second is if, for a study that is reported, we have only selected information about it. And third, the focus here is, how is the data analysis set up? Was just some of the data analysed, just some particular comparisons, for example, focused on, and when and how were they selected? So my example is, let's suppose we've introduced some educational innovation and we've measured the improvement in 10 different subject areas across the school curriculum. Of course there'll be fluctuations between them, variation between them, and we noticed that history showed a particularly marked improvement. Now it could just be that some one of these must be highest, and it happened to be history. But had we in advance planned this focus on history, had there been some reason for predicting that history would have done particularly well, then I'll be rather more impressed if you say, look, this prediction was confirmed and history came out on top. A planned analysis, committed to in advance, yes, let's focus on history, gives us our main conclusion and we can be reasonably confident about that. Contrast that with exploration, where we simply just follow our nose and choose anything that looks particularly interesting. Oh, there's quite a low one. Oh, here's a reasonably high one. And the danger here is that we may just be cherry picking. We may just be looking at, seeking out the things that look most interesting, whereas really they're just random fluctuations. And politicians are notoriously very good at picking out particular statistics that might happen to support their case. Now, exploration can be very valuable because research is always unpredictable, and some really interesting things may appear first as just what might just be little fluctuations. And so you might decide that the result of exploration could be quite interesting speculations, possibly even worth following up in future research. But they're not something we can claim as a firm conclusion. The key question is, was the analysis selected in advance or after seeing the data? Now suppose we read a report that says, I plan to look at history in particular, how can we be guaranteed that that was in fact planned in advance? The best way is if the data analysis plan had been pre-registered, meaning the whole research plan, including the analysis plan, had been lodged at some secure website with a date stamp. And so we could go back and check that, yes, indeed, the plan had been to look at history, and so we can accept that as a planned analysis. Pre-registration of research plans, and we'll say more about this later on in future chapters, is a key feature of open science and much to be encouraged. Exploration can merely be cherry picking, can be just responding to chance. And here are some equivalent expressions for it. Here are the clouds, absolutely random, but we're convinced we can see faces in them. Capitalising on chance, chasing noise, or seeing lumps in the randomness. These are all equivalent and alternative expressions for looking around in the data and seeing something, but maybe it's just a random fluctuation. So seeing faces in the clouds may be appealing, but don't fool yourself. It may just be randomness.